guys, welcome once more to our YouTube channel. In this video we are going to be looking at a problem that came in mathematics paper 1 in the competitive entrance examination into the National Advanced School of Engineering Yaoundé. So we are going to be looking at the 2021 session and we are going to be solving exercise 2. Now for those who haven't watched exercise 1 solution yet, I'm going to add the link to the description and also in the comment section so that you can watch the solution to exercise 1. Alright, so let's begin with the problem, this question. So it was divided into various parts. Part 1, that is question 1. Question 1a says you should express sine raised to the power 4 of x in linear form and it is allocated for 1 mark. Now part B is asking us to integrate an integral. So the integral from 0 to pi ln 4 of the integral from 0 to x of sine cube t cos t dt dx, 1 mark. Now the second part of the equation is asking us to use integration by parts to integrate ln of 2x plus 1 with respect to x in an interval 0 to 1. Now the third part of the equation is divided into 2. The first part is asking us to show that half times the integral from 1 to 2 of 1 on x raised to the power 5 integrated with respect to x is less than or equal to the integral from 1 to 2 of 1 over x raised to the power 4 plus 1 integrated with respect to x, which is less than or equal to the integral from 1 to 2 of 1 over x raised to the power 4 integrated with respect to x. Now the last part, that is the second part of question 3, is asking us to hence deduce the approximate value from the above of the integral from 1 to 2 of 1 over x raised to the power 4 plus 1 dx to 19 times 10 raised to the power negative 2, and it is allocated for 0.5 mark. So let's get started with the solution. So for question 1a, it is asking us to express sine raised to the power 4x in the linear form. So let's follow the steps keenly. Endeavor to subscribe if you have not subscribed yet and turn on your post notifications as well. So the first point, we are going to bring out some basic identities. Sine raised to the power 4 is the same as sine squared, all that squared. As you can see, properties of indices. Now the next thing is that we have the identity cos of 2a is equal to 1 minus 2 sine squared of 2a. From there we can get the sine squared of 2a by subtracting 1 on both sides, dividing by negative 2. We get the sine squared of a to be 1 minus a cos of 2a all divided by 2. Now if you take a to be x, for example, because a is an angle also, we are going to get sine raised to the power 4 as sine squared all squared, but this is sine squared, just replace a with x there, and squaring the denominator you get 4, squaring the numerator you get this. Alright, now our next identity still turns around cosine of 2a, now in terms of the cosine squared of a. So the cosine of 2a is the same as 2 cosine squared of a plus 1. So from there we can get actually minus 1. So let us be careful. So here is supposed to be minus 1, just an error. So you have the cosine of 2a is equal to 2 cosine squared of a minus 1. So from there we can add 1 on both sides and then we divide by 2, and we get the cosine squared of a to be cosine of 2a plus 1 all divided by 2. Now if we take a to be 2x because they are angles, then we can get the cosine squared of 2x to be, replacing a with 2x, we get the cos of 4x plus 1 all divided by 2. Now our essence of doing it was that we need to express this in a linear form, meaning that if it is in terms of trigonometry, the highest power of any trigonometry ratio involved should be 1. But expressing in this form, we have cosine squared, so we need to break down cosine squared again. That's why we have to take it to this form. So from there we can now look for our sine squared by replacing the cosine squared of 2x with its identity, as you can see here. From there, we look for the LCM in the numerator, we send everything to the denominator as well. We just simplify and we get this, the sine raised to the power 4 of x to be 3 on 8 minus half the cosine of 2x plus 1 on 8 the cosine of 4x, and we are done with the A part of question 1. Alright, now the B part is asking us to integrate an integral. So to integrate this, we first of all begin by integrating what is inside before integrating from 0 to pi ln 4. So I will just let f of x to be this integral, that is the integral here. Letting f of x to be it, and we need to integrate it, so I'm going to use integration by substitution. If I take u to be the sine of t, for example, my du is going to give me the cosine of t dt, so I can find the cosine of t dt. That is why I let u to be sine t, so that when I differentiate I have something, we call it derivative around. So from there I can change my limits of integration, because I'm changing the wall from the t wall to the u wall. Now t began from 0 to x, so let us be careful here as well. So t began from 0 right up to x, as you can see. It means u is going to begin from what? From the sine of t right up to the sine of 0 right up to the sine of x, because u is equal to sine t. So when t is 0, you have the sine of 0, which is 0. When t is x, you have the sine of x, which is the sine of x. You leave it like that. So my f of x becomes the integral from 0 to the sine of x. That is replacing the very thing. You have the integral from 0 to the sine of x of, in the place of sine of the sine of t, I'm going to replace it with u, because u was the sine of t. But the integrand here is all cubed, so I cube it. Now in the place of cos t dt, I'm going to replace it with du. Now fundamental theorem of calculus, I add the power and I divide by the power plus 1. So I get u raised to the power 4, all divided by 4 now from 0 to the sine of x. Now I impute my upper limit minus lower limit. The lower limit is just going to give me 0, and the upper limit is going to give me sine raised to the power 4 of x, all divided by 4. So that is my f of x. Now if I let I to be the original integral that I'm finding, then we can clearly see that I is just the integral of f of x from 0 to pi ln 4, and we have gotten f of x already. So it means my I is the integral from 0 to pi ln 4 of sine raised to the power 4 of x, all divided by 4. Now I proved in question A that sine raised to the power 4 of x is equal to this identity. So simple, I'm just going to replace it here. I first of all remove the 1/4 outside. I can multiply the 1/4 and the 1/8 to give me 1 on 32. If I integrate 3, I get 3x. If I integrate 4 cos 2x, I get if I integrate 4 cos 2x, I get 4 divided by 2 sine 2x, which is giving me 2 sine 2x. Now when I integrate cos 4x, we get 1 on 4 sine 4x. Now we are our limit is 0 right up to pi ln 4. Now when we feed 0, everything vanishes, so we just need to feed pi ln 4. So when we feed pi ln 4 here, we get I to be 1 on 32. So we have 3 times pi ln 4, 3 pi ln 4. We feed 2 times pi ln 4 is pi ln 2. The sign of it is 1 times negative 2 becomes negative 2. Now 4 times pi ln 4 is pi, and the sign of it is 0. So this boils down to 0. So at the end, we get our integral I to be 1 on 32 times 3 pi ln 4 minus 2. Alright, so the second part, that's question 2, is asking us to integrate by parts the limit of 2x plus 1 with limits of integration 0 as 1. So I am just going to integrate it indefinitely, and then maybe at your free time you can input the limits of integration. So using integration by parts, we are going to let our u to be the limit of 2x plus 1. From there we get du, meaning we differentiate the interior of the limit and we divide it by the interior itself, and that's du by dx. Let's be careful, du by dx is equal to this. Alright, so from there we now let our dv to be equal to dx. Now to get v, I need to integrate both sides, and my v becomes x. Now my integration by part formula says I is equal to uv minus the integral of v du. So it means this integral that is indefinite, like I said, at the end you can input limits of integration, but it's important that we get it indefinitely first. Alright, so this integral is just uv. Our u is x and our v is ln of 2x plus 1 minus the integral of v du. Our v is x and our du is 2 all over 2x plus 1. So we get this. So now we can do partial fractions here, though there is a shortcut. You can do long division. We take 2x divided by 2x plus 1. But this is a shortcut. I will just, since I have 2x plus 1 in my denominator and I have 2x my numerator, I will try to make my denominator to look like my numerator. So if I want to have 2x plus 1 in the numerator, I will need to add 1 to the numerator and I subtract 1 from it. This gives me 0. I'm still at the same spot. From there now I can separate 2x plus 1 over 2x plus 1, then minus 1 all over 2x plus 1. But now there is a negative sign here, so the negative sign multiplies with this negative sign to give us a positive sign. Now from there, it means that integral is just equal to our x ln 2x plus 1 minus this is going to give us just 1, so you're integrating dx. Now this is going to give us 1 over, that's the integral of 1 over 2x plus 1. So from there, here it maintains. Now when we integrate the x, we get x, there's a negative sign there, and then we'll integrate this. We have half the ln of the absolute value of 2x plus 1 then plus our constant of integration, because I'm doing it indefinitely. Now you can put your limits of integration from 0 to 1 and you get your final response. So that is what you are going to do. Alright, the third part of the problem of the exercise 2, the A part is asking us to show this inequality. So just follow me briefly on what I am going to do, and if the reasoning is okay, you comment. If it is not okay, you also comment. If you have another method, you comment as well in the comment section. Alright, so when I saw the question, it was obvious to solve it, but when I started solving it, it was not obvious again. So I had to think and think and think, and I came out with a method, and you're going to see the method now. So I need to show this. So the very first thing I'm going to show is that all these integrands are bijective in this interval. Next, I am going to show that in this interval, that is the interval 1 to 2, 2x to the power 5 is greater than x to the power 4 plus 1, which is greater than x raised to the power 4. And lastly, I am going to deduce from this second step that 1 over 2x raised to the power 5 is less than or equal to 1 over x raised to the power 4 plus 1, which is less than or equal to 1 over x raised to the power 4. Now, you might be wondering why I am doing that. Now, this is the thing. When you want to solve, like when you want to prove inequalities like this, you begin with the integrands themselves. You create a relationship between the integrands. After creating a relationship between the integrands, you now integrate all through. But now there is a problem. You must integrate, before integrating all through, you need to check if those integrands are continuous and monotonous, that is, if they are bijective in the interval that has been given. That is why I begin by showing that they are bijective, all of them. And then later I try to introduce this inequality, because proving having an inequality between the integrands, right, for a greater than inequality, I will need to reverse the integrands since they are fractions. So if I can show that the denominators, that is 2x raised to the power 5 is greater than x raised to the power 4 plus 1, which is greater than x raised to the power 4, by default, since all of them are greater than 1, because I'm in the interval for x greater than 1, then if I take the reciprocals, I get the inequality less than, because taking the reciprocals all through here, and all of them are greater than 1, then the inequality sign changes automatically. So that is basically what we are going to do. Alright, so first we show that the integrands are bijective. Now, like I explained, it's very important to show that they are bijective, because at the end you need to pass the integral sign throughout, and you cannot pass the integral sign throughout if the function is not continuous in that interval and monotonous as well. So to show that they're bijective, I just need to show that they are monotonous and continuous. So let's begin with the first integral, f of x equals 1 over x raised to the power 5. Now it is defined for all values of x in the set of real numbers excluding 0. Now clearly it is defined in the interval 1 to 2, as you can see, because only 0 makes it undefined. Now since it is a ratio of two polynomials, because 1 is a polynomial, a constant polynomial, x raised to the power 5 is a polynomial as well, a quintic polynomial, and polynomials are continuous in their domain. So clearly f is a ratio between two continuous polynomials, hence it is also continuous. Now we need to check its monotonicity. If it is monotonous, we look for the derivative and then we verify the sign. Now the derivative of 1 over x raised to the power 5 is negative 5 on x raised to the power 6. Now x is in the interval 1 to 2, it means x raised to the power 6 is always positive. So if I take negative 5 divided by a positive number, it will be negative. So I see that the function is monotonous. Specifically, it is monotonic decreasing since its first derivative is less than 0. Now from there I can say it is bijective because it is continuous and monotonous. Next, I take the second function, which is g of x is 1 over x raised to the power 4 plus 1. It is defined for all values of x in the set of real numbers. So clearly it is also defined in a subset of the set of real numbers, because this interval is a subset of the set of real numbers. Now it is also a ratio of two polynomials, and polynomials are continuous on their domain, and it is monotonous because g prime is giving us this, that is g prime is negative 12x raised to the power 3 on x raised to the power 4 plus 1 all squared. Now it is always monotonous because maybe some people might try to look for the turning point here, and you see that the turning point is at x equal to 0, but now 0 is not in our set interval. It means that the g prime can never be 0, so it is monotonous. So specifically it is monotonic decreasing because 12x raised to the power 3 all over x raised to the power 4 plus 1 all squared is always positive because all the values of x are positive. So multiplying by the negative sign makes it negative. So from there we can say it is monotonous, specifically monotonic decreasing. Hence we can say it is bijective because it is continuous and monotonous on the set interval. Now our last is h of x, which is 1 over x raised to the power 4. It is defined for all values of x in the set of real numbers excluding 0. So clearly it is defined in this interval. Now it is also a ratio between two polynomials, and polynomials are continuous in their domain, so our h is continuous. Now let's check its monotonicity. It's almost similar to f of x. The same thing, differentiate and you check the sign. So it is monotonous, specifically monotonic decreasing always in this interval. So we can conclude that it is bijective. So we have shown that these functions are bijective, meaning they are monotonous and they are continuous. Now the next procedure is to show that 2x raised to the power 5 is greater than or equal to x raised to the power 4 plus 1, which is greater than or equal to x raised to the power 4 in this interval for all values of x in this interval. So we are going to begin with this first part, that is showing that 2x raised to the power 5 is greater than or equal to x raised to the power 4 plus 1 for all values of x in this interval. Now this is the most important, that's I can say very tricky here, because it's actually the main brain behind this proof. So follow keenly. First, this is what I need to show. Like I said, it's very difficult to compare two functions, so I try to bring x raised to the power 4 on one side and I get this. Now I am not going to bring one on the other side, because it will be very difficult also to compare a quintic function with 0. So this is what I'm going to do. Alright, remember this sign here is supposed to be greater than or equal to, so take note, not just strictly greater than. So from here I can factor out x raised to the power 4. Here I'm going to get 2x minus 1. So I get x raised to the power 4 into 2x minus 1 is greater than 1. Our essence is to show that this inequality is true. So let us begin. So we are going to show that this left hand side is always greater than 1 for for all values of x in this interval. If we are able to show it, it means that we have shown this, because this is the same as this. The two inequalities are the same, just that this is a degenerate of this. Like we move from this to this other part. This inequality here is supposed to, there's supposed to be an equal to sign there, so we should take note. Alright, my x is in the interval 1 to 2, means that it is bounded. That is 1 is less than or equal to x less than or equal to 2. With that, if we multiply all through by 2, we get 2 is less than or equal to 2x less than or equal to 4. Multiplying all through by 2 here. Now from there, we subtract 1 all through, we get 2 minus 1 is less than or equal to 2x minus 1 less than or equal to 4 minus 1. From there, the lower bound is 1, the middle we get 2x minus 1, and the upper bound is 3. Now, if we multiply all through by x raised to the power 4, so that we are going to get this quantity. So we get x raised to the power 4, since it is positive, the inequality signs remain intact. So we have x raised to the power 4 is less than or equal to x raised to the power 4 times 2x minus 1, which is less than or equal to 3x raised to the power 4. Okay, so from there, we just deal with the red part, because that is where our interest is. We don't care about this other part, because this part still means that the right hand side is greater than the left hand side. So we need something greater than and not less than. So we ignore the less than or equal to 3x raised to the power 4. So we just deal with the part in red. X raised to the power 4 is less than or equal to x raised to the power 4 into 2x minus 1, means that x raised to the power 4 into 2x minus 1 is greater than or equal to x raised to the power 4. Now, you see that we need to show that this quantity is greater than 1. Now, we are at a point where it is greater than x raised to the power 4. So if we just show that x raised to the power 4 is greater than 1, then we can conclude that this quantity is greater than 1 also, because the quantity is greater than x raised to the power 4, and we showing that x raised to the power 4 is greater than 1, then this quantity is greater than 1. Now let's see if x raised to the power 4 is greater than 1. So I will call this maybe equation 1. I will just annotate it. Now x is in the interval. I repeat the same thing. If I take I raise all through to the power 4, they are positive. So 1 raised to the power 4 is 1, x raised to the power 4 is x raised to the power 4, and the 2 raised to the power 4 is 16. Now I'm dealing just with this red part, because the red part is saying that 1 is less than or equal to x raised to the power 4. It means that x raised to the power 4 is greater than or equal to 1, because 1 is less than it. So automatically I can conclude, because x raised to the power 4 into 2x minus 1 is greater than x raised to the power 4, and x raised to the power 4 is greater than 1. So automatically this left hand side here is greater than or equal to 1, and that is what I needed to prove. So from there I can conclude that this inequality is true for all values of x in this interval. Now this other inequality is clear, because we showed this first part. We now need to show this other part, that is x raised to the power 4 plus 1 is greater than or equal to x raised to the power 4. It is clear that it is true, because x raised to the power 4 adding 1 to it will always be greater than itself. So from there we can conclude that this is true. So our second objective has been achieved. Now our third objective is to deduce that for all values of x in this interval, 1 over x raised to the power 5 is less than, not greater than. So all these signs here, just take note, and sorry for the error. So all these signs here are supposed to be less than. So this sign is supposed to be the less than sign, and this sign is supposed to be a less than sign. So let's just take note. Alright, so from there, anyways, you are going to see it in upcoming animations. So since we have x is greater than 1, because x is in the interval 1 to 2, we know it is less than 2, but we know it is also greater than 1. So we just dwell ourselves on x being greater than 1. If x is greater than 1, what does it mean? It means that 2x raised to the power 5 is greater than 1 also. X raised to the power 4 plus 1 is greater than 1 also. X raised to the power 4 is greater than 1. So from there, we establish something which we are going to use this principle. That says that if I have two numbers which are positive real numbers, such that they obey this inequality, that is a is less than b and both of them are less than 1, then the reciprocals, that's 1 over a, will be now greater than 1 over b. So if a and b are less than 1, and A is less than B, then automatically 1 over A will be greater than 1 over B. For example, let's take half and 1/3. I know that 1/3 is less than half, and both of them are less than 1. The 1 over 1/3 is now greater than 1 over half. We can check other examples. So from there, since we have proved this inequality and everything here is greater than 1, it means that the reciprocals will be less. So when I take the reciprocal of 1 over 2 x raised to the power 5, if I want to take the reciprocal here, the inequality sign changes to less than or equal to, and it does not remain as greater than, because we have seen that these guys here are all greater than 1. So from there, since 1 over x raised to the power 5, 1 over x raised to the power 4 plus 1, and 1 over x raised to the power 4 are bijective in that interval, we can now pass the integral sign throughout. So coming with this perspective here, we can integrate all through from 1 to 2. So integrating this, you get this, integrating this, you get this, and integrating this, you get this, and the proof is done. So tell me what you think about my idea. If you have a different idea, you can also post in the comment section. I'll be very happy to see. Alright, the B part of the equation is asking us to deduce the approximate value from above of this integral. So it's going to be good to integrate the upper bound and the lower bound of the integral. So upper bound, integrating it, basic of calculus, you can write this as x raised to the power -4. So integrating, you get 25 times 10 to the -2, or 0.25. Now integrate the lower bound as well. The same thing, x raised to the power -5, you add the power divided by the power plus 1, you get this, and you get 11.7 times 10 to the -2. Now I've helped you to get the upper integral and the lower integral. So do the rest to approximate the value of the middle integral to this precision. Endeavor to subscribe to the channel. If you have difficulties, maybe you have not understood a certain step here, you post your comment in the comment section. We are going to reply to you. After subscription, you turn on your post notifications. Also share the video to your friends, invite them to subscribe to our channel so that they can learn more and more, and together we are going to better the society. Thank you.